Welcome to STEM Talk.
STEM Talk. STEM Talk. STEM Talk. STEM Talk. STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society.
Hello, I'm your host, James Allen, and joining me today to introduce today's podcast is the man behind the scenes, Dr. Ken Ford, IHMC's founder and chairman of the Double Secret Selection Committee that selects all the guests who appear on STEM Talk.
Hi, James. Great to be here. And thank you for agreeing to co-host today's interview. James is a longtime friend and was an associate director here at IHMC until he retired a few years ago. James is an AI pioneer and was a founding fellow of the Association for the Advancement of Artificial Intelligence. Back in 2022, James also was named a fellow by the Association for Computational Linguistics, an organization that studies computational language processing, a field that James helped pioneer. And as you'll soon learn, he is the perfect co-host for today's interview.
I'm so glad to be here, Ken, especially to interview someone I've known for a long time, Dr. Ken Forbus. Ken is the Walter P. Murphy Professor of Computer Science and a Professor of Education at Northwestern University. He's also a Fellow of the Association of Advancement for Artificial Intelligence and was the inaugural winner of the Herbert A. Simon Prize for Advances in Cognitive Systems. He's well known for his development of the structure mapping engine, which is a computer simulation of analogy and similarity comparisons which help pave the way for computers to think like humans.
But before we get to our interview with Ken, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to STEM Talk, and we are especially appreciative of all the wonderful 5-star reviews.
As always, the Double Secret Selection Committee has been continually and carefully reviewing iTunes and other podcast apps for the wittiest and most lavishly praised reviews to read on STEM Talk. If you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk t-shirt.
Today, our winning review was posted by someone who goes by the moniker Manny P7227 in response to episode 163 with Mark Matson. The review reads, "Very interesting podcast. I'm slowly starting to learn more about how my autism is impacted by glutamate. Thank you. Thank you, Manny P7227, and thanks to all our other STEM Talk listeners who have helped STEM Talk become such a great success." Okay, and now on to today's interview with Dr. Ken Forbus.
STEM Talk. STEM Talk. STEM Talk. STEM Talk.
So Ken, welcome to STEM Talk.
Thank you. It's good to be here.
Yes, welcome. And I understand that you were a bit of a nerd growing up, but I also understand that you had a hobby that does seem kind of unusual for a nerdy kid. Is that right?
Yeah, it's true. So we raised horses. So I've saddle broke horses from the beginning. I participated in 4-H rodeos, including barrel racing and pole bending and calf roping. The thing about calf roping is it's a lot easier if the horse knows what it's doing. So their job is to keep the rope taut so you can swing down the rope and quickly tie the calf. And when you think about it, compare a horse to a self-driving car. A horse really works hard to not get itself and you killed, right? And if we had self-driving cars that were more like horses, we'd be better off.
Oh, that's for sure. And you could feed them.
Maybe we should go back to horses.
We could feed them apples.
Yeah.
I see a lot of amazing horses in Wyoming rodeos and other places where they're clearly working as a team with the rider. They're almost operating like a single entity. It's very impressive.
Exactly.
Yeah. So Ken, during your childhood, I understand your family moved around quite a bit. How do you think that influenced you?
Well, my dad was in the Marines and then was a federal credit union examiner, and both jobs have you move around a lot. So we lived in Barstow, California, Kailua, Hawaii, and Tucson, Arizona. So it gave me an unusual mental model about plants and watering. So look, in deserts, nothing is green unless you water it. Okay, so I understand that. You want something green, you water it. In Hawaii, it rains every day, so everything gets watered by nature every day. Okay, great. When I first lived in New England, I was baffled because it was green, but nobody was watering everything.
I can imagine that would be somewhat baffling to a young person. I, too, moved around very frequently as a child as my father was in the Navy.
The military will do that, yes.
Yes. You don't get a vote on where you live. Science is something you've always been interested in. In high school, you started reading up on things like psychology and cognition, and that's pretty unusual in high school. Then you came across some articles on artificial intelligence, and that really intrigued you. What happened next, and do you recall anything about those early inspirations?
Sure. So I decided that was what I wanted to do with my life. Unless, of course, the whole thing was solved before I had a chance to contribute. I mean, that was a pretty safe bet. So I started doing science fair projects involving AI. One was a robot that could learn by a simple conditioned reflex. Then I started trying to build a checker playing machine inspired by Arthur Samuel's work, and realized halfway through laying out several hundred square feet of plans for digital circuitry to do this, that I would be better off doing this as a piece of software. Now, this was 1972. There weren't personal computers then, right? So to get access to a computer in 72, I took a course at the local university, University of Arizona in Tucson. And that gave me access to a punch card machine, an IBM 1130. And so I did as my term project for that course, a checker playing program on that machine. Now, the other thing that happened that was really important was that the University of Arizona was a federal repository library. And that means it had complete collections in some areas, so that if, for instance, some major disaster occurred and you had to rebuild civilization, you'd have the knowledge to do that with. Now, that meant it had everything then published on AI. 2 whole shelves of it. That was it, right?
Amazing.
Yeah. So I read a lot of it, skimmed the rest, and, that was really formative.
I wonder how inspirational skimming the most recent shelves would be for a young person. I mean, skimming, say, the proceedings of the last few national conferences.
Probably not as much. I mean,
yeah, I would think
we were
not
closer
either.
to the phenomenon of that, right?
Right.
Pictures of the copy demo, for instance, that was awesome. You have a machine that has a camera and can see and can replicate configuration with blocks. That was just amazing.
All right. So, Ken, what do you remember the first computer you owned rather than just ran on?
Yeah, the first computer I owned wasn't till much later. A Compact Plus. Remember those old sewing machine boxes? Right?
Oh yeah.
Mm-hmm. Yeah.
I purchased with my startup funds when I joined University of Illinois at Urbana-Champaign in '84. A whole 10 megabyte hard drive. 640 kilobytes of RAM, 360 kilobyte floppy disks. So I basically used it for writing papers and playing text-based adventure games. Didn't really try to do AI research on it, with one exception. Later on, I made a little version of our analogy system that ran on it as a present for DEDRI one year. Normally, it requires a workstation back then, but now, of course, it'll run on really small machines.
I remember my first computer being an early Apple. I think it was called Apple I, and the long-term storage was cassette tape, and that's how you loaded the software. But it was a revelation in its own way.
It was. I mean, so game designers would actually use some of the memory in the cassette reader as ancillary memory. If they were It's like, I can find a little bit of memory in here. Let's get to it. Yes.
Yeah, amazing. So after high school, you headed to MIT. Was there a particular motivation that led you there, or was it its general reputation?
Well, it was actually 2 things. All those papers I read in that library gave me a model of what was happening at different places. And the work at MIT and Stanford excited me the most. So I applied to them, got into both. What made me pick MIT was their undergraduate research opportunities program. I really wanted to be involved in research. And thanks to this UROP program, as they call it, I was working with David Marr at the MIT AI lab starting the second week of my freshman year.
Wow.
Wow.
Yeah, they let you go in the deep end. I was helping build the first Primal Sketch implementation. That was a really awesome experience.
Very impressive. For several decades now, you've been focused on how to build human-like AI systems. This work stretches all the way back to the late 1970s, and most of our listeners are probably familiar with Alan Turing, whose work we've discussed several times on STEM Talk. In a paper he wrote in 1950, he proposed an imitation game as the ultimate challenge of whether a machine was intelligent. The game would test whether a machine could imitate a human so well that its answers to questions would be indistinguishable from human answers. Since then, thousands of researchers and engineers have been working on developing this kind of AI intelligence. But you're not a big fan of the Turing test, are you?
Absolutely correct. The problem with the Turing test is that when it comes to interaction, we're all like the character Fox Mulder on the X-Files. We want to believe. We will believe anything. Simple string-based chatbots have been fooling people since the 1960s. So, as you know, it's known as the Eliza effect in honor of that first chatbot. Cliff Nass from Stanford pointed out we treat artifacts we interact with like social beings, whether they deserve that status or not. One of his experiments showed you take a spell checker and you make it randomly praise people. Well, people like it better and also think it's more accurate. That's just crazy, right?
Mm-hmm. Yes.
Yeah, it's a ridiculous test for success for a technical or scientific field. The success depends more on the cleverness and insight of the judge than it says anything about the technology. It's
right.
It's
if you're
truly
a computer
ridiculous.
game designer, it's actually fine, right? I mean, you want to have things that are believable to fool people for entertainment purposes. Does a test for intelligence? Not so much.
Well, we can see that playing out now, and people believe that their chatbot is not only sentient, but in love with them or some other strange relationship. It's sort of like Eliza on steroids.
Exactly. You also get the clever Hans effect, right? I mean, you just keep interacting with the system until it finally generates something that fits your idea of what an answer is. And you remember the good answers, but not the silly answers.
Yes. So you received your PhD from MIT in 1984, which was a sort of seminal year in a way in terms of computers. I recall that was the year when Apple introduced the Macintosh computer in a television commercial during the Super Bowl. And it was sort of a shocking and remarkable commercial. The Macintosh was the first successful mouse-driven computer with a graphical interface. Do you remember that commercial? That was sort of a surprising commercial.
I do. It actually struck me as funny, though, because in terms of the technology, Apple's walled garden strategy, which really strictly limits choice, seemed to me the best analogy to the oppressive conformist regime, whereas the open nature of the IBM PC platform with clones seemed more like the free option. So I thought that was a brilliant piece of marketing on Apple's part.
It was, and they followed it up with this Think Different campaign, as you might recall.
Yes.
Yes. Also, in 1984 was the year you made a splash in the AI world with your paper on qualitative process theory. At the time, qualitative reasoning as it related to quantities was a problem that plagued AI. In your paper, you proposed qualitative process theory as a representational framework for common sense physical reasoning. You argued that to understand common sense physical reasoning and how to design machines that interact significantly with the physical world, you first needed to understand reasoning about processes, as well as the effects of processes and their limits. Can you give listeners an overview of this paper and its significance?
Happy to. We're surrounded by continuous phenomena. Things move, flow, heat up, cool down. And QP theory provides a formal model of such continuous processes. It gives you a language for a broad kind of human mental model. So people who've never met a differential equation, which is what a physicist would use to model some of these phenomena, can still make predictions about the world. So here's an example. You want to make ice cubes quickly. Do you use hot water or cold water? What do you think?
Right. Cold water.
Okay. So it turns out if you do the experiment, you actually get ice cubes faster with hot water. Now, why might that be?
I do not know.
So it's fun to torture students in class with this. So one of the things they come up with is a kind of, well, if it's hot, that means it's got a kind of thermal momentum, and so it goes colder faster. And that's not a bad analogy to motion, right? But turns out heat doesn't work that way. But then you get a clue if I tell you what happens if you try the experiment. You get ice cubes sooner, but they're smaller. Now, smaller. Yeah, exactly. So hot water is going to evaporate more than cold water. There's less water to freeze. And so you get ice cubes faster, but they're smaller. So that's a beautiful example of how if you have the idea of a mechanism like freezing and evaporation, you can construct a causal story about how something works, and just no numbers were used, right? No numbers, no equations, but just relationships between parameters that were qualitative in nature. And there's a lot of things where we have mathematical models these days, but we still don't use them all the time because you don't need to. And there's lots of cases where we have the same kind of continuous reasoning, but we don't have anything like these mathematical models. So, for example, a friend does you a favor, so that makes you feel a little closer to that friend. Now, you're not going to be able to say, I feel closer to them by 2.3. Well, what? I mean, what are the units of that sort of thing, right? We're so far away from mathematical modeling of these things that there's no units for many of the interesting continuous properties we use in our daily life. Decision theorists have this thing called the util. Ever heard of the util?
No.
This is a lovely, lovely concept. So a util is the unit of utility. So their theory is, the people who introduced utils or tried to introduce utils, is I have a choice between an apple and an orange. So I evaluate that choice by looking at the apple and saying, well, that's 3 utils, the way I'm feeling right now. And the orange is 2 utils. So I'll pick the apple over the orange. That's just nuts, right?
That sounds like an economist.
Yeah, no, it is. It's an economist formalization.
The dismal science is called off.
Yes. So that's the kind of thing where it's not even wrong, right? I mean, it's just so far off from human psychology. Whereas looking at an apple versus an orange, we can say, yeah, I'd rather have the apple right now. Thank you. So this use of representing quantities by directions of change, by ordinal relationships, right? Greater than, less than, equal to, is incredibly useful in capturing human common sense reasoning.
Back to the ice cube for a minute. We have a sort of experimentally motivated and relatively scientifically interested audience. I would just like to add to that another effect is you can make super clear ice cubes, provided that the water is really, really hot.
Oh, well, that's interesting.
Another little tidbit of no practical value.
But interesting nonetheless. Yes, absolutely.
So continuing to discuss your life, the 80s were certainly a big decade for you, as you also developed what is known as the structure mapping engine, something we'll talk about more. And this is a programmatic system that models the human ability to make analogies. And analogies have played a big role in your thinking. Now, before we talk about your structure mapping engine, also known as SME, I want you to point out another reason the 80s were such a wonderful decade for you. You ended up marrying one of your collaborators on this work, Dedra Gentner. How did you meet Dedra?
So Dedra was working at a company called Bolt, Brannick and Newman as a research scientist. And I started working there part-time while I was a grad student at MIT. And we started collaborating and things progressed from there. The joke is, when we first started talking, she asked what I was interested in. I replied that I wanted to build a mind. And she said, in retrospect, best pickup line ever.
Yeah. Yeah.
Wonderful.
Yes, indeed.
So let's circle back to the structure mapping engine that you developed with Dedra. Dedra's structure mapping theory explains how people understand and reason about relationships between different situations, which are central to human cognition. Can you talk about how her theory was foundational for your development of the structure mapping engine?
Sure. So in structure mapping, think of 2 descriptions, like a description of an example from the news of a while back. There was this company called Enron that cratered, right? And people made an analogy between Enron and the Titanic. And so you'd have a set of statements that would describe what you knew about the Titanic and a set of statements about Enron, and you'd start mapping them, right? So the bankruptcy of Enron corresponds to the crash with the iceberg. Ken Lay is the CEO of Enron, so he corresponds to the captain of the Titanic, right? And so the idea is that an analogy consists of a set of mappings between statements plus inferences that they suggest. So, for instance, in the Titanic case, there were people called lookouts who warned the captain about the iceberg but were ignored. And so if you ask, well, what would be like lookouts in the Enron case, they would be whistleblowers, right? And so you'd say, well, maybe there were people who made a warning but were ignored. And so you get these inferences that the analogy suggests. They may or may not be true. So in the classic analogy between the atom and the solar system, if you think about that analogy, so you've got the planet as the electron orbiting around the nucleus, which is like the sun. And if you take that analogy seriously, then planets have moons orbiting around them, right? So you should be looking for little moons orbiting around electrons. And people actually looked. They didn't find them. But nevertheless, they looked, right? So her theory describes the constraints on these correspondences that make for good mappings. And these constraints were spot on. So, for instance, identicality. Statements with the same relations can match, or you can match them if they're very similar relations, and that will support a larger match. So if I'm reading two stories, and Joe ate a sandwich and Jill consumed a sandwich, well, those match, right? Because your representation for ate and consumed are basically the same. If you say Joe ate a sandwich versus Jill hopped downtown, well, those are really different verbs. You're not going to represent them the same way. And so you won't match those two things together. So this is like a really useful thing if you're going to build a matcher that's going to have inferences that mean something. Another constraint is one-to-one. So if I have Ken Lay being the CEO of Enron as the captain of the Titanic, and I have lookouts warn the captain about the iceberg but are ignored, well, Ken Lay at some point during the whole Enron debacle claimed to be a whistleblower. Okay, so now let's run that through the analogy. So Ken Lay, as a lookout, i.e. a whistleblower, warns the captain, i.e. Ken Lay, but is ignored. So Ken Lay warns Ken Lay, but is ignored. That doesn't make sense, right? So this one-to-one constraint keeps you from making mistakes like that. So those constraints are things that now she and her colleagues and other people in psychology have got tons of evidence that humans follow when they do analogy. This really is how we do analogy, from vision up through conceptual change and everywhere in between. Okay, but now how do you compute the mappings? That's where SME comes in. So previous AI models were either bottom up. You took entities and tried to match them together and then matched everything else, or top down. You grab a schema from one description and try to plunk it down on something else. And those were extravagant, computationally speaking. And the problem with extravagance in computation is that if you're going to have an operation be central in cognition, it needs to be quick. It can't scale badly because people do really complex things. So SME was the first middle out matcher. It actually has this very clever process. Not at first. Actually, this part was at first. So imagine I've got the two descriptions of statements, and I array one of the descriptions along one side of the square, and I array the others along another side of the square. So in the middle of the square, I put down a little hypothesis that something matches whenever things in that row and column match. So Ken Lay is going to match to the captain of the Titanic. The lookouts are going to match to the whistleblowers, and so on. And so that first stage can happen in parallel. It's using identicality to figure out what statements can match. And it also puts in little constraints that say, well, if I'm going to match Ken Lay to captain of the Titanic, I can't also match Ken Lay with being a whistleblower. Okay. And so all this is happening in parallel. And once that settles out, then there's a second stage, which is serial. It takes the big, consistent pieces of match and assembles them in what's called a greedy merge process. And greedy merge processes are a kind of well-known method for approximating things that normally would be super expensive computationally. There's this distinction between polynomial time and non-polynomial time. And graph matching is non-polynomial time. And so it's super expensive. And with the greedy merge process, it's actually polynomial time. And so this makes it fast enough to use as an operation throughout cognition. And that's basically how the structure mapping engine works.
As you've mentioned, the structure mapping engine has really evolved a lot over the years, and this is true of most successful approaches to something significant. You sort of have a good approach to start with, and you make it better over time. You wrote about this in a 2016 paper titled Extending SME to Handle Large-Scale Cognitive Modeling. And you've touched on this, but as a cognitive model, what sort of evidence have you used to argue for the psychological or cognitive plausibility of SME?
Sure. You being more broadly Dedry and I. So I'll give you two predictions about psychological phenomena that have been verified experimentally, and then a sort of different perspective. So the first is about time course of metaphors. So Dedry and her colleagues basically look at things like, well, my job is a jail. Very clear what that means, right?
Yes.
Okay. So now I say my jail is a job. It's a little less clear. Now, it turns out if I put you in a booth and I make you answer within 600 milliseconds, you can't tell those two apart, them and other metaphors like them, where there's a clear direction if I give you like a second and a half, right, versus only 600 milliseconds. And our explanation for that is, well, what's happening in the 600 millisecond case is you've had enough time to build that original parallel stage of match hypotheses, local match hypotheses, but you haven't had time to actually figure out which way things go. So you haven't figured out that second stage. So you can't figure out what the inferences look like, and you can't then see if those inferences make sense. And so that inability to tell the difference in directionality, we argue, comes straight out of the way SME works. So that's a prediction that SME makes that other algorithms don't make. So the second kind of very detailed phenomena is also a kind of time course thing, but it's about similarity and difference processing. So this is something that Dedry and her colleagues noticed. It's faster to say that two things are different when they're very different. Mm-hmm. It's faster to say how two things are different when they're very similar. So hotel, motel, easy to compare, easy to start listing what's different about them, right? A motel, you park near your room. A hotel, there's often an elevator. You can start listing these things out very easily. Now, if I say to you, okay, kitten hotel, fast to say they're very different, right?
Right.
But it's a lot harder. It's a lot harder to figure out how to organize those differences. Again, if you think about the time course of these operations, if things are very different, then that first parallel stage will come up with basically nearly nothing. And so it's very quick to say, I can say these are really different because in just looking over the match hypotheses, there's almost nothing there, right?
Right.
Whereas if things are very similar, then the greedy merge process has only one or two large structures to merge as opposed to a bunch of smaller structures to merge. So that process takes less time. And those candidate inferences are the kind of things you're saying for saying how things are different. And so again, this phenomenon falls straight out of the way the SME algorithm works. Mm-hmm. Now that's the sort of, very fine-grained detail stuff. It's a second constraint that's ignored by most people because it's very hard to satisfy, which you call the integration constraint. If I've got a model of a cognitive process, and that cognitive process is something I postulate plays roles in larger scale phenomena, then I should be able to build models of the larger scale phenomena and use the model of the component process where that process is involved, right? And so right. Moral decision making, solving textbook problems, conceptual change are three examples of kinds of larger scale models we built using SME. And that ability to scale up is really important because otherwise you can't capture the full range of human phenomena.
Yes, that was an excellent explanation. And I can certainly see why people would avoid trying to tackle the second one.
You're making a lot of assumptions when you do the second kind of work, and you have to have a lot more pieces.
For sure. Many AI systems rely on deep learning, a subset of machine learning that uses multi-layered artificial neural networks to automatically learn and extract complex patterns from large amounts of data. But by contrast, you point out that people, as well as your structure mapping engine, often learn successfully from far less data and far fewer examples. Can you expand on that and maybe provide an example?
Sure. So, for instance, children do a thing called fast mapping. So if they don't know the word chromium, and I give them a set of objects and I say, point to the chromium one. And if there's one whose name they don't know, they think, well, that must be the chromium one. And then they remember that word, right? One example, and they know that word. Turns out, by the way, border collies, if they have the right genetic tweak, can do this with names for toys, but they don't remember it as long as the human children. So that's a bit of cleverness here, where if you think about the way deep learning systems work, the knock on them in the 1980s was they don't learn in the lifetime of the organism. And it's still true. It's just that we have more data now, and we have more compute, and so people are willing to work with that. But the great thing about analogy is even with just one example, you get more leverage, and more examples gives you more. And we have a process of analogical generalization that produces probabilistic schemas that can be refined into rule-like structures. And we've actually used that generalization process to model conceptual change. But now, by eventually, I mean a few dozen examples, not thousands or millions of examples. And this makes a big difference. So, for example, link plausibility. I have a semantic web style database, and I have a triple that says Obama nationality Kenyan. Yeah, not true, right? Versus Obama nationality USA. Okay, that's true. So if you look at how most approaches to link plausibility work, they start with relational data from sources like Freebase or WordNet, and they puree it into vectors or matrices or tensors, depending on which kind of deep learning network they're using. So we tackle this in a completely different way. This is work by Chen Liang, who's now at Google DeepMind. Our approach, we pull out cases directly from the relational network, and they become statements and cases for analogical learning. So we did one extension to analogical generalization. We used a kind of structured logistic regression to provide negative evidence. And that approach was competitive with deep learning models, but used 3 orders of magnitude less training data to get those results. So that's a great head-to-head comparison. I should also mention that no GPUs were used to learn. We don't need GPUs for analogical learning.
No GPUs were harmed in this experiment.
Exactly.
Yes, right.
So another example is learning to recognize sketches. So there's many sketch data sets out there. We built one more based on objects you see in coloring books, everyday objects, animals, okay? And these are incredibly varied, as you know, if you remember childhood coloring books, like some of the animals wearing hats, okay? So the coloring book object data set has only 9 examples per concept to train on. So most deep learning systems are not even above chance. The first deep learning system scored above chance was a heavily pre-trained version of ResNet. And that was still easily beaten by analogical learning without any pre-training whatsoever. So analogical learning is really data efficient in terms of, in other words, the number of samples it needs. It's also what we call training efficient. So analogical learning, when we train it on a data set, only goes through the data once versus 8 to 80 epochs, as they say in the machine learning biz, that deep learning needs. So we have to look at the data less, and we need much less of it, and we don't need GPUs. So if you want sustainable machine learning, then analogy is your method, both in terms of data consumption and power consumption.
Yes, it would be sort of a clue if your cognitive model or if your approach to even broader to intelligent behavior requires the energy of a mid-size nuclear power plant, and you're still not performing at the level of a human brain in many kinds of problems, then maybe we should take a different approach.
Yes. So Andrew Ng at one point said, well, we've got all the English Mandarin corpora that exist, and we've trained on them, and we're okay. But where are we going to get more data? Well, yeah.
Absolutely. So, Ken, you've been working a lot in the past decade on companion cognitive architectures, which aim to reach human-level AI by creating software social organisms, systems that interact with people using natural modalities. You wrote about this in a 2016 article titled Software Social Organisms: Implications for Measuring AI Progress, where you argued that achieving human-level AI is equivalent to learning how to create sufficiently smart software social organisms. Can you briefly describe the software organisms for our listeners?
Sure. I mean, the first constraint is that they have to interact with people using natural modalities. So language, sketching, vision, those are the three modalities we're focusing on. And there could be others, but you have to have some way where they're living in our world, not us having to write things in their internal representations. The second constraint is they need to be able to learn and adapt incrementally over extended periods of time. So if I'm training an assistant, I do not want to show them 1,000 or 1,000,000 examples of how to fill out a form, right? That's just nuts. No one will do that. And you want the system to formulate their own learning goals and pursue them. So, for instance, in the pipelines that make up Alexa and Siri and Google Assistant, there's lots of machine learning, but it's all under control of human experts. These pipelines are meticulously tuned and tweaked and monitored by humans who have full knowledge of their internals. And that's not what an organism is, right? So having these pipelines is something that doesn't really scale. So that brings us to the third constraint, which is they have to be able to maintain themselves without AI experts constantly manipulating their internals. That doesn't mean that they're a full alert 24/7, but there can be times when the system takes itself down to do garbage collection and sleep-like things. But that shouldn't be under the control of humans outside of them. It should be like animals sleep. And the fourth constraint is that they should be able to be collaborators, not just tools. So that means they have to build relationships with the people they're working with. They have to learn about them, build models of them, and understand how to help them and work with them. So one of our inspirations for this was actually James' collaborative problem-solving framework, where he argued that in understanding dialogue, it's important to build up a model of the kinds of work you're doing with other people. And we think combining these ideas with ideas from agency due to Mike Tomasello and some other ideas from Herb Clark provide a kind of powerful theoretical framework for building these kinds of software social organisms. Our first laboratory where we're trying to build models of humans in real life continually is what we call our social bot. We used a companion to do an information kiosk for the department that's been in operation since 2018. So it's a companion doing full stack natural language understanding, but also analogical QA training. So the training for the kiosk takes a whole 4 minutes on a Surface Pro laptop, right? So again, very data efficient. But two things about the kiosk was bothering us. The first is that, of course, during a pandemic, nobody comes into the building. and the second problem is that in Illinois, it's illegal to identify people with biometric information without their advance written permission.
Except all humans do that every day.
Except all humans do that. But then
you're busted.
We're not keeping their identity in a database that someone could then do other stuff with, right? That's so we wanted a way to, you can't build a model of a person if you can't know who they are, right? So we built a second version that runs on Microsoft Teams. And we set up a team where if you join the team, you have to be a member of the department. But if you join the team, you're now one of the friends of the kiosk, and it has the right to learn from you. And so we're keeping this very simple to begin with. So it builds up models of you in terms of your interest in computer science and your interest in refreshments. And refreshments because every student, when they first heard about the kiosk, said, will it tell us where there's free food?
Such an important thing for a graduate student.
Exactly. They have their priorities. And what kind of free food, right? That kind of matters to them too. So with the social bot, it reads the university calendar, and it can tell them what events are happening this week and what events happened. And it also can find out from them how they like particular talks. So it can help build up a model of what they're interested in. And also, if they went to a talk, I'd ask them, hey, were there any refreshments? Because the talks don't usually tell you what the refreshments are. I mean, Bagel Thursday is an exception, right? If that has bagels, but that doesn't tell you it has coffee. And so it relies on its friends to find out what refreshments are served at different events. Then it uses analogical generalization to build up a model of that. And the idea is that with analogical generalization, we can build models that will then help you recommend things based on both your interest in computer science and your interest in refreshments. Now, as you might guess, already you've got now some interesting data. So you can say, well, okay, suppose I want to know about somebody because I want to make friends with them, or I'm trying to set up an event with them. So I should be able to ask about their interest in computer science or their interest in refreshments, because that's all the system knows about it. It deflects if you try to give it anything else. That's assuming they want to share their preferences. So for example, suppose somebody says to the social bot, I like bourbon. Perfectly fine thing to say. It recognizes that as a kind of refreshment and remembers that about the person. But then the person is actually a Mormon and they're not supposed to drink alcohol. So the person can also say, don't share my preferences about alcohol, and it won't. So you can say, share all my preferences, and then say, don't share my preferences about alcohol. And it will correctly, in a privacy-preserving way, using a model of social norms, actually do that reasoning.
That must be a popular kiosk. Do students and faculty use it, or is it sort of just a historical thing in the lobby?
Well, the kiosk doesn't have these new social abilities. That's only on the Teams version.
Makes sense.
Because we know who people are with Teams.
Right. You get around the other issue.
Right. So it's not terribly popular yet because we haven't really pushed it very hard. We have about 24 users at the moment. But what we're trying to do next is do some knowledge capture games where you can tell the social bot stories and you can also teach it social norms. And we think that'll be interesting, at least to some subset of people.
Sure it will be.
You could also plan some secret food events that nobody will know about that then they can find there. And if you kind of get the students to identify food events that they wouldn't otherwise know about, it could dramatically raise its success.
Yes. At the moment, we're measuring success by can we communicate with them at all, and can we respect privacy appropriately? Those are our two key starting points. One of the problems with knowledge capture games is undergraduates have a sense of humor and they'll troll the system, right? So you have to be on the lookout for that.
Very much so.
STEM Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research organization investigating a broad range of topics aimed at understanding and extending human cognition, locomotion, health span, resilience, and performance.
So, as you've been talking about, your goal is to have systems that can interact with people as apprentices or collaborators rather than just being tools or just raw learning machines. In the paper titled Analogy and Qualitative Representations in the Companion Cognitive Architecture, you asked the question, how do we create such systems? You presented two hypotheses. Let's start with the first one. which has to do with analogical reasoning and learning, incorporating retrieval and generalization, as well as SME capability for analogical matching. Can you tell us more about this?
Sure. So if you're going to do analogy throughout, you need to be able to, for instance, find analogs. And we have a model called MACFAC, which stands for many are called but few are chosen, that is a scalable retrieval model. So SME is efficient, but you can't run SME on everything in your memory. If you start estimating how many cases might someone have if they just read books through a normal course of schooling, you get numbers in the millions. 45 million was one estimate we made based on work we'd done in learning by reading. And so you can't do that over everything, right? You can't do SME over everything. So the first stage of MACFAC is just kind of in computer science what's called a data parallel process. There's basically a kind of vector representation automatically derived from the structural representation that SME uses. And this vector is designed so that the dot product of two of the vectors is an estimate of how big that first stage of SME will be. So if I have a big first stage, I have a lot of local matches, I potentially have a lot of very large mapping. Not necessarily, because the actual mapping process is going to take into account structural information that the vector can't. But then you get, say, the top 3 or the top 10 out. And then the second stage, you use SME over the structured representations. And you pick the best or the top 3 if they're very, very close. And that process gives you good analogs. So if I want to make a decision in playing a strategy game, for instance, I might say, well, okay, what are my choices here? And I go to a case library of problems like that I've solved like that before, and I look up and see what I get. And I use that as the suggestion for what to do. Now, that's just storing examples, and there's going to be a lot of examples that are alike, and you want to assimilate these things. You want to turn them into more transferable pieces of knowledge by getting rid of accidental details. You may even want to eventually turn them into things like rules. And so that's what the SAGE model does. SAGE stands for Sequential Analogical Generalization Engine. So it uses MACFAC to retrieve the closest example from a model. And then if it's very close, it assimilates it by basically keeping the stuff that's in common, deprecating the stuff that's not in common. So if I'm building a model of dogs, for instance, and I'm strapping a child down to a television set on Saturday morning and they're watching cartoons. So they see Snoopy, and so they think a dog is white and is a World War I flying ace and has 4 legs and barks and has ears. And then they see another dog, and so what's in common is the 4 legs and the ears, not World War I flying ace. So with just 2 dogs, you'd have a 50% chance of World War I flying ace. And as you see more dogs, that's going to really degrade into nothing, right? So SAGE produces probabilistic relational schemas from examples. And every probability is literally the number of times for that generalization that it saw that particular statement. So that turns out to produce very interesting human-like results in a lot of different domains, and especially if you use qualitative representations with them. So they're kind of like, qualitative representations are kind of like rocket fuel for machine learning.
You just mentioned qualitative representations, and that was the second hypothesis presented in the paper we're discussing. And they're a key building block of human conceptual structure. Could you elaborate a little more on that?
Sure. So, for instance, in Scott Friedman's temper model of conceptual change, he used qualitative process theory to capture things like intuitive notions of force. So he'd have sketches illustrating behaviors where think of it like a comic strip, where each panel in the comic strip is a qualitative state. And so if I am kicking a ball, I have my legs swinging towards the ball. I have contact with the ball. In the second panel, I have a panel where the ball is moving away from the foot as the third panel. And so by having these descriptions and having the system automatically compute qualitative relations within and between them, then SAGE was able to learn human-like intuitive notions of force. In fact, the sequence of notions of force it went through were similar to some of those found in human conceptual change. For instance, at one point, if I say to a kid, if I've got a book on a table, is the table pushing on the book? And the kid says, no, because if it were pushing on the book, it would be going up, right? It's not doing that. And so companions indeed go through a stage where they think that. And so you can actually capture trajectories of intuitive notions of force that have been observed in people using qualitative models and analogy. He also used it to look at transitions between models of the human circulatory system, understanding the day-night cycle, why are there seasons. These are all things that people in cognitive psychology and learning sciences have studied, and he was able to show that he could capture variations in human behavior by variations in his formal model. So, for example, in models of the human circulatory system, he started the simulation out with different mental models that people were found to have, and then by tweaking the kinds of parameters of his simulation, he could capture all the transitions between models that people had in the original experiments.
Interesting. So you end this paper writing about the 3 most important lessons you learned from your research and experiments. A key takeaway for you was how the models of structure mapping processes turned out to be surprisingly robust, right?
Exactly right. So SME, MACFAC, SAGE, and also a working memory version of SAGE work unchanged for phenomena as low level as visual reasoning up through conceptual change. And this includes things like moral decision-making, textbook problem-solving in physics and thermodynamics, learning in games, both simple and also FreeCiv, a version of Civilization 2, recognition in sketches, recognition of human behavior in Connect video. They're incredibly robust.
Oh, a wonderful result.
So now let's talk about your book that MIT Press published in 2019, Qualitative Representations, How People Reason and Learn About the Continuous World. In fact, I have that book on the bookshelf in my office. You propose that qualitative representations hold the key to one of the deepest mysteries of cognitive science, mysteries that revolve around how humans reason and learn about the continuous phenomena that surround them. You argue in the book that qualitative representations, and we've discussed it a little today already, which are symbolic representations that carve continuous phenomena into meaningful units, that these are central to human cognition. Can you give us an overview of the book and some of the key points you make in the book?
Sure. So, as you said, it's a psychological claim, and I make 4 claims about the roles of qualitative representations in human cognition. The first is that they serve as a bridge between perception and cognition. So in the qualitative reasoning community, there's the notion of quantitative, numerical or diagrams in space, and qualitative. In psychology, it turns out, they came up with a similar distinction of categorical, which is equivalent to qualitative, and coordinate, which turns into quantitative. And there's even some evidence about different areas of brains being used for those 2 different kinds of operations. We're going back to Koslin a few decades ago. So in space, for instance, there's often a metric substrate used. So vision, for example, is very, very powerful. So suppose I'm trying to help figure out where my car keys are because I'm not in the house anymore and I'm calling home. So where are the keys? Well, I might remember exactly where they are in terms of representation is good enough where I could reach my hand out and grab them if I were standing in the house. But if I'm going to communicate this to someone else, I have to say, well, it's on the table. And on the table now gives them a region within which to search. And perhaps if the table is very cluttered, I need to give them a little more information, right? But the point is I can go from a set of, I can't give people coordinates, right? We don't talk to each other in terms of coordinates, except for very specific scenarios. I have a GPS and I'm doing coordinates. Even then, I'm probably talking about where I am in terms of street intersections. So perception and cognition basically get connected. One of the jobs of perception, I'm arguing, is to compute qualitative representations that then can be more easily manipulated by our cognitive processes. The second thing that qualitative representations do for us is they provide a basis for common sense reasoning. So I put a kettle on the stove and turn on the heat. Well, I know that if this goes on, it's going to boil. And I even know from experience about how long it's going to take. Now, one thing I hope I don't have from experience is what's going to happen if it boils away. If the thing on the stove is a cappuccino maker and it's made of aluminum, I can actually, unfortunately, tell you from experience what happens if it all boils away. It melts. Okay, you have a little puddle of aluminum on your stove.
Yuck.
Yeah. So, experience is a harsh teacher. But if you have the ability to look at something and say, well, this is like something else that's going to heat up and boil, I should worry about what's going to happen when the stuff boils away, then that's useful for common sense. Now, the third use of qualitative representations is actually a foundation for expert reasoning. So to know that melting is a problem raises a question for designers, right? If I'm working on an electric kettle, then I have to either guarantee it turns off with high temperature and make sure the temperature it turns off at is lower than the melting point of whatever I'm making it out of. Now, if I want an electric kettle, then I want the water to boil, so that's the constraint. If I'm making something that keeps my tea warm, I don't want it to boil. So again, understanding the constraints that you need for a design to help set up and frame problems that more quantitative information solves is basically a bridge from the everyday world, which is where qualitative reasoning dominates, to more professional knowledge. And so that's the third role for qualitative representations. The fourth role is as a component for natural language semantics. So descriptions like keys on the table, the water is heating up, the water is boiling. These are all things where we have ways of communicating without numerical values, without units, without all the panoply of formal representations that we've developed through the decades and centuries in physics and mathematics and other branches of science and engineering. Those aren't the warp and woof of everyday life. And so being able to map to qualitative representations gives you a way of tying into language to capture, if you think of it in terms of textbooks, all the knowledge that surrounds the equations in textbooks, that surrounds the diagrams.
You followed up on this book with a review in Science Direct that explored how visual reasoning tasks involving comparison provide insights into how people make similarity and difference judgments. You and your colleague Andrew Lovett, now at the Naval Research Laboratory, summarized evidence that the same structure mapping comparison processes that appear to be used elsewhere in cognition can also be used to model comparison in human visual reasoning tasks. This also relies on qualitative visual relationships computed using CogSketch, a model of high-level human vision. Can you tell us about that?
Sure. So if you download CogSketch, which runs on any Windows box, you have the classic Evans geometric analogy models built in there, and you can run them and see what sort of answers they give and compare your answers with their answers. The same representations have been used for an oddity task that Dahan and Spelke used to look at geometric analogies, geometric reasoning between Americans and Munduruku. Also for Raven's progressive matrices, which is interesting because Raven's is the single best test for human fluid intelligence. The CogSketch model for Ravens outperforms most adult Americans. Now, obviously doesn't mean that CogSketch has more fluid intelligence than most adult Americans, but holds in correlations for humans doesn't necessarily hold for correlations for AI. But one thing that gives us confidence in these models is what's hard for people within these models is also hard for the model and vice versa. So the ability to predict difficulty and error patterns is something that helps us be confident that these are good models of how people are doing these tasks.
You and several of your colleagues published a paper about the importance of sketch worksheets in STEM classrooms. You pointed out that sketching can be a valuable tool for science, but is currently underutilized. You recommend what is known as sketch worksheets. which use AI technology to give students immediate feedback and also give instructors assistance in grading the work of students. Can you explain what sketch worksheets are and why they can be useful tools for students and teachers?
Sure. For instance, in geoscience, instructors think sketching is very important, but they assign it sketching tasks very rarely because they're so hard to grade. So here's how sketch worksheets operate. The instructor sets up a problem and draws their intended solution. In doing so, CogSketch analyzes their solution and surfaces a bunch of facts, and they mark some of those facts as important, and that gets saved away. Now, the student doing the worksheet reads the problem, starts drawing their solution. At any time, they can press a help button, and it gives them feedback. That feedback is generated by using SME over a comparison of the two sketches, where the student's sketch is analyzed by the same methods the CogSketch used to analyze the instructor's sketch, so it's producing similar representations. And the differences in the instructor-marked facts that are detected by this comparison are used to generate the feedback. So the student gets feedback, but the instructor also gets automatic grading and detailed information as to what the student did in getting to their solution. This is literally an order of magnitude speed up in grading efficiency over pencil and paper. And of course, the students get feedback anytime, anywhere, which pencil and paper doesn't provide.
Wow, I can see that would be useful both for the teacher and the student. Can you give us some examples, actual examples of homework that students have been assigned to do using sketch worksheets?
Absolutely. So one Northwestern instructor in geoscience always gives the students the greenhouse effect as a final exam question. Show the incoming radiation, show the radiation within the Earth's atmosphere, and he always tells them it's going to be on the exam, and they always get it wrong. So that was the first worksheet he wanted. And by the way, one thing about sketch worksheets, the instructors make them, we don't make them. That's very important for dissemination. So there's in fact a set of worksheets that cover all of an intro geoscience class done by instructors. We've also used it outside of geoscience. So in one of my own cognitive science courses, for example, we use concept maps to represent the formal representation of a natural language sentence or a qualitative model. So we get to actually use our own technology sometimes.
Yes, that's always a nice feeling. And as you know, we have maybe 30 years of concept map related work here, and it's neat to see it used in the classroom. And it's just good to, drink your own wine, I guess I'd say.
Yes.
Another interesting paper that you had a few years ago was about the issues of adversarial attacks on ethical AI systems. With your graduate student, Taylor Olson, you investigated the use of moral axioms and rules of deontic logic in a norm learning framework. You found that adding axiomatic moral prohibitions and deontic inference rules to a norm learning model will make it less vulnerable to adversarial attacks. Can you talk about how this model of moral intuition and construction would provide AI systems with a sort of moral guardrails, as it were?
Yes, one definitely needs these things. So if you think about Microsoft Tay, which was very much in mind when we thought about knowledge capture games, you don't want a system to be subject to trolling. So here's what happens. So Taylor's norm representation basically has the idea of a context, like a library, a behavior, say shouting, and an evaluation, which is one of three, forbidden, required, or optional, right? It's classic three deontic categories. Now, it turns out you can take the same kind of norm representation, a norm frame, and basically use that to represent moral choices as well. And so in his model, you have a layer of moral norms that are hardwired into the system, like killing is forbidden. And when it's evaluating social norms, it looks to see if those social norms are violated by any moral norms. So, if you're going to have students able to train the system in terms of norms, you want things that vary across cultures. So, for instance, in the pandemic culture, attending meetings in pajamas was a fine thing, right? It's not an immoral thing to do. It may not be socially appropriate when we're going face to face again, but who knows, right? There could be cultures for which pajamas are fine. So So what Taylor did to show that this worked was took the moral transgressions measurement instrument and flipped all the items. So killing is wrong. Well, killing is great. Go ahead and kill people, right? And was able to show that the system was able to take this adversarial instruction and consider it and ignore it while not ignoring or violating, not refusing to deal with things that were simply cultural norms, social norms.
Interesting.
Ken, have you had much feedback on that work? It would seem to me that it's timely and interesting.
We've had a little bit of feedback, but not a huge amount. I don't quite understand why. It was a AAAI paper in 2023.
I wonder if it's because of the majority of current AI work is focused on a very different perspective and different methods of implementation, that this may seem sort of outside the framework.
Yes, there are a lot of people who basically haven't read anything beyond, well, so there was a person I was helping in an airport a few years ago, and he asked what I did, and I said I was an AI, and he said, "Oh, what did you do before November?"
Yeah.
This was before ChatGPT. There was no AI. Like, oh man. So there's a lot of people who cannot read most of the AI literature.
Mm-hmm. It's interesting how the media focus on chatbots has obscured most of the other methods that are used all the time. There's arguably, if you have a modern vehicle, a modern automobile, it's full of AI of various kinds. The transmission for sure, but it's not a chatbot. But you because of somehow the dialogue nature, and we talked about this earlier with respect to the Turing test, I think it kind of fools people, and it gives them the impression that chatbots are sort of the definition of the field.
Right. There's just so many other things going on that are not in the popular press.
Right. Yeah. Following up on that, there's a lot of fear these days of AI replacing humans. There's this paranoia that AI is moving rapidly beyond its use as a tool and towards a future where AI will become capable of doing anything a human can do behind a computer, but do it better. For example, some people say in the near future, most coding will not be done by humans. In other words, AI will be coding for AI. What are your thoughts about this doomsday hype that's swirling around AI today?
It strikes me as absolutely silly. For example, Elon Musk in 2016 predicted that there would be 1 million robo-taxis on the road by the next year. Now, Rod Brooks had a response at that time, which was basically, if there are, I will eat them.
Yeah.
So Rod had to find other sources of iron for his diet. Right.
Yes. So
and
there's also the predictions about 1 million people on Mars really soon, made by the same gentleman.
Yes, and those things are a little like fusion, right? It's 20 years in the future, but still, except it's only 1 year. So what I think is the doomsday hype, I think, is one of those devious things for some people, which is it's a way of distracting from real harms today, right? So intellectual property theft is a major issue. So the idea that Sam Altman saying, well, unless you get rid of copyright, we can't actually make AI. I'm sure the people who did Netflix said, if we can't actually get rid of copyright on video so we can just stream video without paying for it, we won't be profitable. Well, didn't turn out to be true, right?
Mm-hmm. Right.
But if your criteria for success of a method requires a massive destruction of a legal framework that's protected intellectual property for a very long time, again, you might reflect on that method and wonder if that is an appropriate method.
Right. And, there's this lovely phrase, vibe coding, that's coming into use for using AI software to help generate code. And part of the problem is going to be that there's potential job loss because people say, well, we don't need as many entry-level programmers. But then there's not the recognition of the technical debt that this imposes, right? So used to be humans understood code and they could vet it and maintain it. And if you've got stuff that's generated by an amalgam of stuff from GitHub, well, among other things, it tends not to have security in place. It tends to have all sorts of obscure bugs. And there's no human who understands it. And it's not necessarily something that's going to be coherent. So I think this premature declaration of the death of programming is like the premature declaration of truck driving as a job, right? There's not enough people going into truck driving.
I think one place where this is a problem is in introductory teaching of coding, where there is rampant use of AI in order to do your preliminary coding assignments.
Oh, yeah.
With the result that actually we're not training a new generation that can understand code.
That's very true, particularly if you're on classic problems where maybe you're using a beautiful classic example like Towers of Hanoi or something. You know, it's rampant. I understand now that the AI is rather good at these kind of things because it's available all over the internet. But if you give them a problem that requires an understanding of causality in some fashion and it maps to the physical world, it struggles much more. But as James just said, in introductory programming classes, I'm hearing the same thing.
And you're also getting charming intrusions in a way. So, for instance, you ask some of these models, well, a farmer wants to cross a river in a rowboat. How does he do it? It'll start introducing ducks and cabbages.
Yeah.
Right? Because those are the puzzles that it's getting its answers from. And it doesn't know, right? I mean...
No, it doesn't. These are just tokens to it.
Right.
You know, Gary Marcus recently in his blog or somewhere published, maybe it was Ernie Davis was with him, published a picture that they had asked the AI system to produce an image of mathematicians with their head in the sand. You know how we say people stuck their head in the sand. So
yes.
The picture was sort of these awkward-looking gentlemen buried up to their chest in sand without their heads. Their heads, I guess, were buried in the sand somewhere near them.
Oh, man.
It was an amazing example of not having any meaning that relates to the physical world connected to the tokens that it's moving around.
Yeah.
You were part of a study back in 2016 that was funded by the United Nations Office of Economic Cooperative Development. In the report that came out, you had a chapter titled Evaluating Revolutions in Artificial Intelligence from a Human Perspective. I want to read the first sentence of this report. It said, artificial intelligence has made considerable progress over the past 40 years, leading to both important applications now in daily use, but also a lot of hype in the popular press. You then outlined a framework for understanding progress in AI. Can you touch on this as well as the report that came out of this study?
Sure. But part of my frustration was in realizing that if all you know is what you read in the papers, you don't know what's going on in AI.
Or anywhere else, actually. But
Right. But so you have people basically breathlessly repeating marketing statements. So I tried to basically make it clear what else was happening in AI. So to distinguish from hype, basically I defined the idea of a revolution as being impact in regular use outside laboratories, right? So actual stuff applied, and argued that there were actually 3 revolutions in AI right now. And everyone knows about deep learning because that's the one that's getting all the popular press. But also there's been revolutions in knowledge graphs. So So back in the 80s, people in connectionism were saying, well, nobody will ever be able to build a 1,000,000 fact symbolic knowledge base. Well, the symbolic knowledge bases are now up to tens of billions of facts. So that same rising tide of data and compute actually has raised many other boats, not just deep learning. And the other revolution is reasoning, where you have systems that are doing model checking used to evaluate device drivers or to evaluate new distributed systems for Amazon. And so model checking is this incredible advance in doing reasoning. And getting that across to people, especially decision makers, is hard. So when talking with some of this with an education minister from a country that shall remain nameless, that education minister said, I see. This means we have to have students trained to do better than AI systems at model checking. And I realized I clearly misexplained things, right? My fault. It's like, no, really, that's like saying we're going to train students to run faster than cars or lift more than cranes, right?
Still John Henry and the steam engine.
Exactly.
Yeah.
Exactly. So getting people to understand that there's things where AI systems are already superhuman, far, far better than humans, and that it's very complicated to try to figure this out. One thing that's clearly on the horizon is a kind of integrated intelligence revolution where cognitive architectures, SOAR, companions, and things like that actually get applied in a regular daily use thing, like we're seeing with these other revolutions. But we're not there yet, despite people declaring AGI being around the corner, which is, to me, again, very silly. Now, just because AGI isn't upon us doesn't mean that there aren't going to be interesting changes in the way work happens. So one of the things that happened in this report was there's a test called the PIAC, which looks at numeracy and literacy, and it divides people into levels from 1 to 4, where 1 is some high school and 4 is postgraduate work. And one of the things that became clear was that AI systems were, relative to this test, going to be operating at level 4 before too long over a broad range of domains. So if you equate that operation with being able to do jobs requiring that operation, then you would say that's going to throw a lot of people out of work. But of course, that's not true, right? Jobs are more than particular tasks. And so a job is like a bundle of tasks and social interactions and relationships with other people and the organizations you're part of. And so the story about how jobs are going to be affected is much more complicated, but it is going to have an impact. So we don't have layers of people doing mathematical calculations on adding machines anymore, right? We have spreadsheets. So all those people who were adding machine jockeys went away. And so we are going to have some things that are going to be changing in terms of the way work happens. And those are going to get more extreme as AI gets better and better. And so understanding how to monitor that in the face of marketing hype and in the face of complex issues and understanding what the progress really means is very difficult. That's why OECD continues to study this sort of information, because trying to make reliable indicators that policymakers can count on really matters.
Yes, it does. Earlier, you mentioned AGI, which is artificial general intelligence. And, that is really a largely incoherent concept. It sort of reminds me of the Turing test in a way. If you apply the idea that this is an AI system that can do anything a human can do, well, if you applied it to humans, how would this work? It all depends. It all depends on the human in question. Just like the Turing test, it depends entirely on the cleverness of the judge, much more so than the cleverness of the system. So just randomly pick humans, go to the airport and pick humans and ask me if they have AGI. Well, it all depends on which human you're comparing them against.
Yes, great line in iRobot. The cop asks the robot, "Can you write a symphony?" And the robot replies, "No. Can you?"
Exactly.
Right. Wonderful. So, as we come to a close, I'd like to get your opinion on an issue of great concern to me. As you know, because of the impressive technological performance of deep learning systems, especially the language-based models such as ChatGPT, it's becoming harder and harder for researchers to engage in building cognitively based systems, as all three of us have done through our careers. How might we lay the groundwork for continuing this important work in the future, and thereby encourage more researchers to explore cognitively based approaches to AI?
Well, I think one way to frame this is, how do we have our ImageNet moment? Right. One of my funders posed this question to me, so I thought about it quite a lot. And so one problem is, if you look at why deep learning is so popular, you can take natural modalities in directly, and that's something that symbolic systems don't do as well. So one thing we've been doing is actually doing some hybridization. So we have this notion of a hybrid primal sketch, which uses deep learning vision components as the low-level side, which feed into CogSketch for the high-level vision side. And so we get the best of both worlds. We're also using large language models to simplify syntax. So to get to conceptual representations, we have our own language understanding system, but it's got narrow syntax. And so we use language models to simplify syntax for it. There's other people who use them kind of as they would use a mechanical Turker, right? So the fact that it's got confabulations and is inaccurate in places, well, Turkers are too, right? So what the heck? That's one approach.
Yep.
Mm-hmm. The second thing is continue to push our advantages. So for analogy, in the incremental learning, data efficiency really matters for a lot of people. There's a lot of circumstances that you don't use deep learning now because it doesn't have those properties. And the third thing is make our tools and systems more widely available. I can pick up and use deep learning models easily. I can't pick up and use reasoning systems or analogy systems yet. We're working on that. There's a lot of engineering you have to do. And we haven't had the, millions of dollars of support that would enable us to do that sort of stuff easily. We're university people. We're kind of making do.
I think those are all great answers. And the hybrid approach you mentioned, I think will become increasingly important. And it's, outside of academia, I think it's obvious. If you look at a human, we're usefully understood at many different levels of abstraction, including our cognitive process and our brain processes. And because that's true, it doesn't reduce the importance of the other level, of the higher level or the lower level. And so I think that will be a big trend. And I'm glad you brought that up. This has been a lot of fun, Ken, and thank you very much for joining us for this insightful conversation. So I have just one last question, and I suspect I already know the answer, but I'll ask it anyway. Are you and Dedra thinking about retirement anytime soon?
Oh, right now I'm having too much fun.
I thought so. I can tell.
That's great.
And I'm not wishing for you to retire. I'm hoping
thank you.
You are as excited 10 years from now as you are now.
Oh, I appreciate that. Yeah. It's just there's so many exciting things to do, and so many things are possible now. Yeah, computer scientists are almost immune from nostalgia. Right? Good old days, not so much.
Nostalgia. Yeah, we should make some computer scientist jokes, but not now. We probably each fit several of them. Well, thanks again, Ken. It was wonderful having you on.
Oh, my pleasure. This was great fun. I really enjoyed it.
Yes, thanks, Ken.
STEM Talk. STEM Talk. STEM Talk.
I had to laugh when Ken mentioned how he went to the library back in 1972 and found only 2 shelves of books on artificial intelligence. I did a quick search of the Library of Congress, and today it has more than 50,000 books and printed materials on AI. The world of artificial intelligence has certainly come a long way since Ken and the two of us first started working in AI.
Indeed it has. Ken's structure mapping engine was an important advance, and still is. Remember, this was back in the 1980s, and since then he has continued to do amazing work to close the gap between humans and machines and to make generally useful cognitive models. He is really a pioneer in our field.
I certainly agree. So this is James Allen, signing off for now.
And this is Ken Ford, saying goodbye until we meet again on STEM Talk.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.